100 years ago, Heisenberg proposed the uncertainty principle. It tells us that the position and momentum of a particle cannot be precisely measured at the same time. This conflicts with human experience. We always intuitively think that the position and momentum of a particle are independent variables. Although they may both change over time, it seems there should always be a way to determine their values at a specific moment. With the development of quantum mechanics, physicists have gained a deeper understanding of the uncertainty principle. It is actually not about measurement. It arises from the wave nature of particles. The position and momentum of a particle fundamentally do not have definite values. In this video, we will explain the origin of the uncertainty principle starting from the wave nature of particles, provide a complete mathematical proof of the principle, and guide you to truly understand the essence of the uncertainty principle. To understand the uncertainty principle, the first concept we need to grasp is the wave function. In classical mechanics, the position of a particle in a spatial dimension is represented by a single number, which is its coordinate value. In quantum mechanics, however, the position state of a particle is no longer a single value but is represented by a function. This function takes position coordinates as its variables, with each coordinate corresponding to a complex number. This function is called the position wave function of the particle. We can draw an auxiliary spindle and wrap the position wave function around its surface to more clearly display the shape of the wave function. The Schrödinger equation governs the natural evolution of the wave function. As a result, the position wave function of a particle changes over time. Besides the Schrödinger equation, the wave function collapses when measured. For position measurement, the wave function collapses at a specific point x, representing the measurement result as x. For an identical wave function, where the particle is in exactly the same state, the collapse point during each measurement is not fixed but appears randomly at different positions. This demonstrates that even for particles in an identical state, the measurement results are uncertain each time. The probability density of the wave function collapsing at point x is the square of the modulus of the wave function at that point. Using this formula, as long as we know the wave function, we can draw the probability distribution curve of the measurement results. The expectation value of x refers to the average value of measurement results. If the probability distribution curve is symmetric, then the expectation value of x is the midpoint of the symmetry. Having understood the position wave function and its statistical relationship with measurement results, let's move to the next step in understanding the uncertainty principle. The uncertainty principle describes the relationship between delta x and delta p. We often refer to delta x as the position uncertainty. But how exactly is it defined? In statistics, delta x is known as the standard deviation of x. Its square equals the integral over the x-axis of the squared distance from each sample point to the expectation value, weighted by the probability density. By substituting the relationship between probability density and the wave function, we can calculate the standard deviation of x from the wave function. If we plot the wave function and the length of twice the standard deviation on the x-axis, we can better visualize their relationship. First, when the wave function shifts horizontally, the standard deviation remains unchanged. Similarly, when only the phase of the wave function changes while its modulus remains the same, the standard deviation is also unaffected. This property, that the standard deviation doesn't change with shifts or phase alterations of the wave function, will be important in the derivations later. However, when the wave function broadens, the standard deviation increases. When the wave function narrows, the standard deviation decreases. The wave function can be made arbitrarily narrow, and the standard deviation of x can be made arbitrarily small. So why does the uncertainty principle insist that the product of delta x and delta p must be greater than a constant? To answer this, we need to understand momentum and its standard deviation. Just like position in quantum mechanics, the momentum of a particle is no longer a single value but is represented by a function. This function uses momentum as its variable, with each momentum value corresponding to a complex number. The function is called the momentum wave function of the particle. Similarly, when we measure the momentum of a particle, the momentum wave function collapses. The collapse point is random, and its position represents the measurement result. The probability of the wave function collapsing at a certain point equals the square of the modulus of the wave function at that point. From this, we can write the formula to calculate the standard deviation of momentum. By applying the momentum wave function, we can determine the standard deviation of momentum. At this point, we have obtained both the standard deviation of momentum and the standard deviation of position. According to the uncertainty principle, the product of these two standard deviations is greater than a constant. The reason behind this can be explained using the relationship between the position wave function and the momentum wave function. In classical mechanics, the position and momentum of a particle are two independent physical quantities, represented by real numbers indicating their values at a given moment. In quantum mechanics, however, the position and momentum of a particle are represented by functions, the position wave function and the momentum wave function. These two wave functions are not independent. Applying a Fourier transform to the position wave function gives us the momentum wave function, and applying an inverse Fourier transform to the momentum wave function gives us the position wave function. You might wonder why the Fourier transform of position corresponds to momentum. This is a complex and abstract question that we will not delve into deeply in this video. A simplified classical interpretation is that the Schrödinger equation governs the evolution of both the position and momentum wave functions. For classical particles, the rate of overall movement of the position wave function is given by the expectation value of the momentum wave function divided by the particle's mass, while the velocity of the momentum wave function is determined by the spatial gradient of the potential energy. This shows that the momentum wave function is consistent with the classical definition of momentum in terms of its physical meaning. We will explore this topic further in future videos. The position wave function and momentum wave function are the positional and momentum representations of the spatial state of a particle, respectively. Knowing one wave function allows us to derive the other. From an informational perspective, each wave function contains the full information about the particle's spatial state, just expressed in different representations. There are many profound correlations between the source and target functions of the Fourier transform. For example, the wavelength of one function corresponds to the expectation value of the other. This relationship is described by the famous de Broglie wavelength formula for matter waves. Additionally, the standard deviations of the two wave functions are related due to the Fourier transform. This is the origin of Heisenberg's uncertainty principle. Now that we understand the fundamental basis of the uncertainty principle, we will next mathematically prove the inequality that relates the standard deviations of position and momentum. Proving the uncertainty principle using operators and commutators is quite concise, but it involves many abstract mathematical concepts. Therefore, I have decided to use the Fourier transform relationship as the basis for the proof. The process is a bit intricate, but I hope to explain it clearly. What we already know includes the definitions of the standard deviations for position and momentum, as well as the Fourier transform relationship between the two wave functions. Our goal is to prove that the product of the two standard deviations is greater than a constant. Using symbolic notation for the Fourier transform relationship makes it more concise. Let's first list the definitions and theorems that will be used in the proof. For wave functions, there is a normalization requirement, that is, the integral of the probability density equals 1. Additionally, the wave function must decay sufficiently fast at infinity. Next, some properties of the Fourier transform are needed. Given a function and its Fourier transform, we can determine the Fourier transforms of the function after translation, phase shift, or differentiation. Additionally, Plancherel's theorem states that the integral of the squared modulus of a function is equal to the integral of the squared modulus of its Fourier transform. It is worth noting that the Fourier transform formula used in quantum mechanics differs from the one commonly used in mathematics due to differences in coefficients. Consequently, some coefficients in the formulas listed here may not match those found in mathematical textbooks. We will also use the integral form of the Cauchy-Schwarz inequality. This is key to proving the inequality in the uncertainty principle. The first step is to simplify what we aim to prove. These two Fourier transform theorems tell us that shifting the position wave function or the momentum wave function only affects the phase of the other, without altering their standard deviations. Thus, we can shift both wave functions so that their expectation values are 0 without changing their standard deviations. We only need to prove the uncertainty principle for these 0 expectation value functions. Hence, we can simplify the proof by assuming the expectation values are 0. Start with the normalization formula for the wave function. Rewrite the squared modulus as the product of a complex number and its conjugate. Perform integration by parts. Due to the properties of the wave function at infinity, the first term equals 0 and can be omitted. Expand the differentiation. The integrand becomes twice the real part of the inner product of two complex numbers, which is less than or equal to twice the product of their moduli. Since the integrand is a non-negative real number, absolute values can be introduced outside the integral. Define two functions, f, x, and g, x. Write the integrand as the product of f, x, and g, x. Apply the Cauchy-Schwarz inequality. Now, what remains to be proven is that these two terms are equal to the standard deviations of x and p, respectively. The first term is straightforward. Substitute the definition of f, x, and we directly obtain the standard deviation of x. The calculation of the second term is slightly more complex. We start by substituting the definition of g, x. Here, we use the Fourier transform of a derivative and apply Plancherel's theorem to equate the integrals of the squared moduli. This transforms the integrand into the momentum representation. After some rearrangement, we obtain the standard deviation of momentum. Thus, we have mathematically proven the uncertainty principle for position and momentum. From this proof, we can also see that uncertainty arises from the relationship between different representations of a particle's state, independent of measurement error or disturbance. In fact, uncertainty is not limited to position and momentum, it also exists between other physical quantities. For example, when studying the spin state of a particle, uncertainty also arises between different representations of spin. This will be covered in future videos.